Okay, and welcome back. So, as I talked about in the last lecture, or part one, we're looking at observational studies, and under that umbrella, we have cohort and case control. Now, I'm just highlighting case control is one of the observational studies of interest for us. In lecture 4.2, we're going to spend more time talking about it. Again, this has a retrospective look to it. It looks similar to the retrospective cohort design, but it is not the same thing. I like this figure here. As an epidemiologist, you are a detective. And so at the start of the study, whether you're doing something prospective or a clinical trial, you're looking into the future. And if you are doing a retrospective cohort or a case control, you are looking at the past or into the past to help answer your question. So let's finish things off here talking about ways to express and compare risk. First up is absolute risk. This is the probability of an event in a population under study. So this is essentially incidence, and we've talked about incidence already, and that being the number of new cases over a period of time divided by the number of people in that group. Example: death rate due to smoking. The absolute risk in lung cancer in smokers is approximately 3 to 4 per 1,000. The death rate of lung cancers in non-smokers, we can make a comparison now, is about 14 per 100,000, according to numbers presented in the textbook. So, what is that additional risk of disease following exposure above what other people would experience who were not exposed? So that's the attributable risk. So with the attributable risk, we're looking at the absolute risk of disease in exposed persons minus the absolute risk in non-exposed persons. Let's do the math now. So if we're looking at that smokers example, our absolute risk there, subtract from it the non-smokers, and then we get the attributable risk. This is also known as the risk difference. Relative risk is probably the most common way that you're going to see the risk magnitude reported in literature that is within your discipline. Relative risk is how many more times likely is an exposed person or persons, how much more likely are they going to be to get the disease relative to non-exposed persons. So this is the relative risk, also known as the risk ratio. And it's the incidence in the exposed divided by the incidence in the non-exposed. And here's how you could do the math if you did a contingency table, a 2x2 table. Now, this is really important because I think in this week's homework, I have you calculate something. Look at where it says risk factor, yes or no. Basically, the top line there, risk factor, means who do you think is at risk? So that's important. When you look at a problem, who do you think is at a greater risk? Is it the person that eats a poor diet? Is it the person that doesn't exercise? Is it the person that has substance abuse disorder? Is it the person that doesn't get sleep? That would be the at-risk or the exposed group. They go in the top row. And then the bottom row would be everybody else. And then you would then put in the correct number in the cell associated with the disease. How many people got the disease? So there's the math on how to lay out the ABCD. And then here's the math how to calculate the relative risk. And so it's the incidence in the exposed divided by the incidence in the non-exposed. What does the relative risk score you get, what does that mean? Well, if the value is greater than 1.0, and you find that there's a statistically significant relationship, because in the future we will do things using stat software, then if it's above 1.0, that means what you thought was a risk factor actually was a risk factor. So let's say it's 2.5. That means individuals who have risk factor X are 2.5 times more likely to experience a disease or injury than those in the reference group. If, on the other hand, and I've had this happen before, the relative risk is less than 1.0, then that means what you thought was a risk factor either was not a risk factor or actually maybe even had a protective effect to it. Let's say you're looking at a particular dietary strategy, and let's say you assume that the carnivore diet would put people at greater risk of heart disease, and you compared it to the Mediterranean diet, but turns out you find that the Mediterranean diet was actually worse. Well, what would happen is if you put carnivore diet data in that at-risk row, you might get something like a 0.5, meaning the Mediterranean diet was the riskier one, or the carnivore diet had a protective effect. If the relative risk equals 1, then that means there's no difference between groups. Now, in a table, you'll see researchers list 1.0 value as the value for the comparison or the reference group or the referent group. Different ways of saying it. Here's an example of doing the math by hand. As you see here, there's two types of people doing exercise. There are those who do excessive exercise and those who do moderate exercise. We might hypothesize that those who do excessive exercise are at greater risk for sudden death. And in this particular data set, they are almost 7 times more likely to incur sudden death than those who do moderate levels of exercise. And then here is an example using incidence density. So to do the math here, take 16 divided by the number of person years, the 2,354. That gives you 0.0068. And so then you make it per 1,000 person years to get that there's 6.8 deaths per 1,000 person years. You can take the 6.8 divided by the 0.9 to then give you your relative risk using incidence density. The population attributable risk. So, how much does a risk factor contribute to the overall rates of disease in groups of people rather than individuals? It's important for determining risk factors and identifying which are trivial for the overall health of a population. The population attributable fraction, this is the fraction of disease occurrence in a population associated with a particular risk factor. And then there is the general formula for it. Not something that I've seen commonly presented within the physical therapy or athletic training literature that I commonly read. Many other variables involved beyond just exposure and disease. These variables can cause unwanted artificial change in the observed relationship between exposure and disease, leading to incorrect conclusions about the relationship. They can modify the magnitude of the exposure-disease relationship too. Variables that are part of a system being studied but are not the exposure and disease of primary interest are extraneous variables. So, for example, a study of exercise and sudden death, extraneous variables are things like age, BMI, coexisting diseases, or the possession of other cardiovascular disease risk factors. Another term for extraneous variables are the covariates, and these you would need to consider when you do any statistical analyses. How you might be able to account for that is to use the odds ratio. Now, the odds ratio is something that is used for case control studies, but you will see them used for cohort studies too. The crude odds ratio measures of effect, not just adjusted for other variables. Let me rephrase that. I kind of said that awkwardly there. The crude odds ratio is a measure of risk magnitude, but it's just focused on what you're looking at. So if we were thinking about the excessive exercisers versus moderate exercisers, if we did a crude odds ratio, it would give us a measurement that's similar to the relative risk. It doesn't take into account or adjust for other variables. The adjusted odds ratio would. So it accounts for statistically for other variables that might affect that relationship. And here's an example from a Rocky Mountain student, one of the original early leaders in Rocky Mountain. What's the word I'm looking for? One of the first students to go through at that time was the Doctor of Science program. So early on, the Doctor of Science program was the terminal academic degree that Rocky Mountain offered, and then it evolved into the PhD program that you're involved with now. So what we see here is from this particular paper by Dr. Phil Plisky, in Table 5, he's presenting crude odds ratios. And so to get those, he would have done a regression, because you can get a crude odds ratio looking at two variables, but here he's got a reference variable. In this case, like when we look at grade 9 was the reference variable because we see that 1.0. And then it's comparing the risk of injury in comparison to being a ninth grader. And so we can see those risks. Do any of them rise to statistical significance? As you think about that there, what would we want to be thinking about? We would want to see the 95% confidence interval all above 1.0. And none of those do. They all cross 1.0. So by definition, it is not statistically significant. We can see an example of one there, the anterior reach distance difference. Those that are equal to or greater than 4 centimeters, those individuals were 2.3 times more likely to get injured, and we see that the 95% confidence interval did not include 1.0. Now, Table 6 in that same paper also did some adjusting, and an adjusted odds ratio is presented here. And again, these took into account other potential variables. All right, that's the end of lecture 4.1. When you're ready, go on to 4.2.